So this is Jeff Hamrick at Rhodes College again. When we were last talking to one another, I guess, I was collecting 1,000 measures, 1,000 additional measures by sampling without replacement samples of size 263. Because that's a fair amount of work. It takes a minute or two for Fathom to do this, and so we cut off the last screencast, and this is a continuation of the first part of that last screencast. I've now collected the 1,000 measures, and I'm going to table off of this measures box to take a look at the measures I've collected. I did indeed collect not only 1,000, but also the 5 that were created by default when you right-click on this box to collect measures initially. And as I'm looking through these measures, I'm seeing that an awful lot of them are taking on values right around the supposedly special test score in this group of students exposed to the open book policy. So I'm thinking that it's not in fact all that unusual that there's a difference between students exposed to the open book and closed book test policy. In fact, that these two test scores, these two mean test scores could have been created just by random chance. Let's quantify that a little bit further. Let's talk through that by dragging down a graph, and I'm going to drag down this collection of measures that we've created, and I'm going to create a dot plot. Okay, very often dot plots in this class that are created by repeatedly generating measures are going to have this bell curve shape. I want to plot the measure taken with respect to my initial set of data, not data from sampling without replacement, but just from the original set of data. My open book group had a mean of 191.357. That's where that value stands within this randomization distribution. It is not very far in the right tail or very far in the left tail. Therefore, I'm going to conclude that there's a high probability that the apparent difference in these two groups' mean test scores is due to random chance. What would we estimate that probability to be? Well, it would be the relative proportion of dots that lie in this right section of the randomization distribution. Let's measure that exactly, though, by defining a measure on the set of all measures. So I'm going to go to my measures box by double-clicking on it and then clicking the measures tab, and I'm going to create a measure on the set of measures called, as we're typically going to do in this class, the empirical p-value. The formula is going to be the count of all the mean test scores that are as weird as or weirder than what we saw in our original set of data. So that's going to be 191.357. Okay, I don't just want the count of the dots that exceed that threshold. I want to divide it by the total number of dots, because what I want is an estimate of a probability value. And we estimate a p-value, that is, we have an empirical p-value of about 38%. So 38% is a very large probability if you ask me. It's way larger than 5%. It's way, way, way larger than 1%. So an appropriate interpretation of this empirical p-value is that roughly 38% of reproductions of this experiment in which there's no difference between open and closed book labels, that is, there's no distinction between the open book status and the closed book status, roughly 38% of those simulated experiments create results as strange as or stranger than what we saw in our original experiment. Therefore, our original experiment does not really suggest any connection between an open book policy and a closed book policy and this difference in test score. So while there may be some small effect here, it's not large enough for us to conclude that there's a meaningful connection between testing policy and the average final examination score.